This video is about Kepler's first law, which states that planets orbit the Sun in an elliptical orbit with the Sun at one of the foci. And in this video, we'll also talk about such concepts as semi-major axis and so forth, eccentricity and other interesting terms such as that. So let's go ahead and begin, but I want to give you a disclaimer right off the bat, and that is when we look at the orbit of most planets, we say it's in the shape of an ellipse, but really it's probably pretty close to this. Now, if you look at this, you can tell that this object here, this orbit, almost looks like a circle. And in fact, most planetary orbits are very, very close to the circle. But the point is that they're not a perfect circle, and they are elliptical instead. So to give you the concepts to help you understand, the planet's orbit, what we do is we massively exaggerate the orbits to look something like this, which is kind of egg-shaped or oval-shaped, and it's none of the planetary orbits are like this at all. So you'll just have to get used to this idea that to show you the concept, we exaggerate the the eccentricity or the shape of the orbit to look more like an ellipse. But in reality, it's very, very close to a circle, but not quite a perfect circle. So let's go ahead and talk a little bit about this ellipse. Now I drew this on, I just drew this ellipse, but in reality, every ellipse has what we call focal points. Okay, I'll show you a little video later on, and if you've read, you've seen that one way of creating ellipses to put down two thumbtacks, get a string, and draw, if you make the string into a loop, draw what the shape becomes when you use your pen against the edge of the string where it allows you to go. It's going to be a shape exactly like this. So when you pull your thumbtacks out, then you're going to get two focal points just like this. So what I'm going to do here is, remember Kepler's law says that the Sun resides at one of the ellipses. So let me go ahead and grab everything here, and we'll try to move this up here and put the Sun, in a sense, right there at one of the ellipses. Now you might ask, what is at this other ellipse? What is out there in space at this other ellipse? If I got rid of it, it turns out that's the way it is. There's actually nothing there at all. There's not a black hole. There's nothing weird. There's absolutely nothing physically there. The mathematics, the physics works just fine, but there's nothing there physically in space. Now what we're going to do is have that reappear because we need to help us understand what ellipses are all about. So let me change colors here so we can take a look at some of the essential features of an ellipse. First of all, if we go all the way across here from one edge through both foci, this is a foci here and this is a foci here, then we have what's called the major axis. And then if we go, say, along this light blue here, and we go from the shortest end to the shortest end, we have what's called the minor axis. And basically it's just taking the major axis and splitting it in two. Now we're not so interested in the minor axis, but I'm going to keep it up there for just a second. Okay, what would happen if we take this orange line, which we call the major axis, and we divide it by 2? If we divide it by 2, then we have, what I'm drawing here in red on top of the orange, half of the major axis. So we take the major axis, whatever its length is, we could measure it with a ruler if we wanted to, and divide it by 2, we have what's called the semi-major axis. So I'll go ahead and call this here then the semi-major axis. Very good. So that's actually one of the more important features of an ellipse is the distance of the semi-major axis. Now, the other important feature of any ellipse is the distance between the foci, and later on we're going to adjust that to half the distance between the foci. But okay, you remember where my foci are? There's one right there and there's one right there. So we could go ahead and talk about this distance right here as the distance between the foci. But it turns out, just like we take the major axis and cut it in two, we're going to take the distance between the foci, and we're going to cut it in two as well. So let's go ahead and do this with a nice little shade of purple. And if I take this distance that I used earlier and I cut it in half, I'm going to get what I have here in purple here, like that. So we have half the distance between the foci. So it kind of sounds a little weird that we do something like that, but if you think about it, like I can draw another shape down here. Let me change the colors. It's a little easier to see. Okay, that's supposed to be a circle. I know it doesn't look quite like a circle, but how do we measure, like what describes a circle? A circle is described by its radius, right? And so when we have equations like what's the circumference, it's 2 pi r, what's the area, it's pi r squared. You don't need to memorize these values or anything, but the point is you've probably heard of pi r squared before, right? The area is given in some equation that goes as the radius. But let me ask you, if you were actually measuring, if you wanted to measure the radius, could you do it directly? You could not do it directly, right? We know this is here is the radius, but most likely what you're going to do is you're going to go all the way across with like a ruler because you don't know where the center is, and you're going to end up measuring the diameter. So what did we do with the diameter? We cut it in two and then use that in our formulas over here. Well, that's what we did right here. We took half the distance between the major axis, and we took half the distance to the major axis. We took half the distance between the foci. So we're doing the same thing as what we've seen done before. So what are we going to be doing with these values that we have? And let's concentrate on those values that we've been talking about. The ones that we're most interested in then are half the distance between the foci and what we call the semi-major axis. All right, what we're going to try to do is we are going to determine the eccentricity ellipse. The eccentricity, we use the symbol or the letter E to stand for the eccentricity. Let's spell it out here. Now the eccentricity, turns out, is a ratio of two numbers. It turns out it's C divided by A. Now it really doesn't matter what C and A are. You just have to remember that the eccentricity is always between 0 and 1, or from 0 to 1. That means that the small number, whatever C is, the small number has to go upstairs. Now take a look again at our two things that are of interest to us. We've got a semi-major axis that stretches all the way across here, and then we have half the distance between the foci, which is right here. Now which one is the smaller value? It's going to be half the distance between the foci. So it turns out that's what goes upstairs. Half distance between the foci is what C is equal to. So I'll write out C here. And then the semi-major axis, the length of the semi-major axis, is what's equal to A. That's up here. Okay, so we can see that we have a small number divided by a larger number, and that's what tells us what the eccentricity of a circle is. If we do that correctly, we should get an eccentricity between 0 and 1. So let's go ahead and try to determine what the eccentricity is of our particular ellipse that we've drawn here. I have a little ruler here, and let's say my ruler is measured in centimeters. I'm going to bring it up here, and let's go ahead and first try to find out what half the distance is between the foci. So assuming this is in centimeters, maybe we have perhaps from right here to about right there, that'd be half the distance between the foci. We've got, say, about 0.7. So the eccentricity of our ellipse then is 0.7 centimeters upstairs, and now we need to get what the semi-major axis is. So I'll pull this down a little bit so we can see our semi-major axis a little bit better, maybe to about right there. And if we start again from right here and go all the way to about right over here, it looks like it's about 2.4. So our semi-major axis is 2.4. Therefore, this eccentricity is 0.7 divided by 2.4. The small number is upstairs, and the answer would be 0.29. Let's just make it equal to 0.3. Now the centimeters over the centimeters cancel, so the eccentricity is unitless. You don't put any, it's not inches or centimeters or anything like that. It's just simply equal to 0.3. So it turns out our ellipse here that I've drawn for you is equal to 0.3. I would like to show you one other thing too that I think will help you out when you're trying to measure the eccentricity. Because you notice what we did is we found half the distance between the foci and we found half the major axis. That's what we call the semi-major axis. But since it seems like we're taking half of everything, and perhaps we don't need to do that. In other words, let's try this another way. I'm not trying to confuse you. I'm just saying it's much easier to measure the entire length of the major axis and the entire distance between the foci. Let me show you what I mean here. Let's go up here to the foci, and if I hold this correctly, looks like I'm a little bit off here, but I'm just going to say, as it should be, what would be the distance between the foci? Well, from here to about right there is going to be 1.4 centimeters, right? And then what about the length of our major axis? Not the semi, but the major. Have a hard time kind of lining up the ruler here, but from here to about here might be somewhere perhaps around 4.8 centimeters. Now you can see how some of these numbers are related. I'll do this in yellow because 1.4 here is very similar to 0.7. The distance is just 1/2, and 4.8 is very similar to 2.4. So what happens when I take these guys and divide them by each other? 1.4 divided by 4.8. Guess what you're going to get? 0.3. So the eccentricity is equal to 0.3. The point I'm trying to make here is that when you're actually using a ruler, you can choose to go half the distance between the foci, okay, that is from here to there, and divide it by the semi-major axis, that's from here to over here. That's what we did down here. Or if you want to cheat a little bit, you can also go all the way across to get the major axis. That's from here all the way over there. That's what we did down here. And then you can just go find the actual distance between the foci themselves. That's what we did right here. That's the distance between the foci right here. And guess what? You get the same answer both times. Let's resume our discussion here and talk about a variety of different ellipses. Recall that our ellipse that we solved for up here was equal to 0.3. Now, what would happen if we were working with an ellipse where the foci were much closer together? Compare that with what we have upstairs. That means that if we're talking about half the distance between the foci, we know, for instance here, that C is going to be a very small number. That's why I'm dividing it like such. Okay, small little c, and I'm going to divide it by a nice good size A. And what happens if we get these foci even closer together than they were before? Then C is getting even smaller than before. So what happens is when we move our foci together, it looks like our eccentricities then are approaching 0. Well, let's go ahead and take the case where the two foci are right on top of each other. If we use a string and tie it in a loop, something like this, tie it in a loop, and then we put a pin here to draw what that particular shape would be, change the color here, let's say brown. If we are constricted by that loop, then we are going to form what are we going to form here? We're going to form what's called a circle. So the smallest the eccentricity can be is when C approaches 0. And when C is equal to 0, the two foci are on top of each other, and you have 0 upstairs. This becomes 0, so now the eccentricity also becomes 0. So a circle occurs when the eccentricity is equal to 0. But what happens if I take my two foci here, and instead of moving them closer together, I move them further and further apart? Let's say something like that. And again, if we were using string or thread to form a loop, we would see here with our loop, we've got a fair amount of room here. And so if I draw my pen is like this. And let me change the colors here. Let's say my pen is a nice blue color like this. I would have kind of an ellipse that looks like this, probably not too different than what I see upstairs. But I'm going to take that same loop now, this loop that we have here, and move it over here. Now, one thing you'll see is that it's a lot more taut, right? See how it's a lot more taut? And when I take my blue pen and I try to draw a nice ellipse with that, I just don't have a lot of freedom of movement. I might have something that looks like this. Okay? So there's some obvious differences here. E is equal to C divided by A. But what we're doing is when we stretch out our foci, it turns out that C is getting to be about the same size as A. As we pull it further and further apart, this would be our minor axis, excuse me. This would be our major axis. Here would be half the distance of a major axis, which is the semi. And then here would be half the distance between the foci, right? Just like what we have upstairs, okay? Well, we see that this value here is almost the same thing as that value down there for the semi-major axis. In other words, C is getting very, very close to A. Now, when you have the same number upstairs as you have downstairs, what do you get? That's right. The eccentricity is going to be 1. And eventually you can pull these foci apart so far that all your string can do is be super taut. And when you run your pen between your strings, you're just going to go back and forth, back and forth, back and forth, back and forth. And what does that form? A straight line. So what we're seeing is that the eccentricity has limits. The smallest it can be is 0. The largest it can be is 1. At 0, it's a circle. At 1, it's a flat line. So what we have here is somewhere in between, back at our original ellipse, is a point 3. So let's look at a variety of ellipses here. Let's first start with the top one. Can you guess what the eccentricity of this top object is? Remember that the sun would be somewhere here in the middle. If you put a thumbtack down there and another foci, you would see they'd be practically on top of each other. So if E equals C over A, C is practically equal to 0. If you take half the distance between the foci, and the foci are practically on top of each other, we see here that the eccentricity is pretty much equal to 0. And that is a circle. Now I want to remind you again that even though we draw ellipses down here that are fairly eccentric, for the planets, basically the eccentricities are very, very close to 0. In fact, for the Earth, the eccentricity is equal to 0.017. So when you look at it from above, as we're doing here, it looks practically like a 0, but yet actually it's an ellipse. And it shows has some major effects such as perihelion. Sometimes it's closer to one foci, and then aphelion is when it's farther from that same foci where the sun is located. So sometimes it's close, sometimes a little further away, and this is due to the eccentricity of the Earth's orbit. So let's pay attention to the next one here. I haven't drawn where the foci are. When I draw these on the computer, it doesn't show where the foci are, but my guess is that they're somewhere like this. You can see that they're a little bit more separated. Perhaps the eccentricity here would be somewhere around maybe 0.2. And then here, again, the foci are quite a bit further apart, and perhaps the eccentricity is maybe, what do you think, maybe about 0.4. And then finally, down here at the bottom is quite interesting because the foci are widely separated. So when we think about the eccentricity being half the distance between the foci divided by the semi-major axis, oh, I don't know, perhaps we've got the minor axis right here. This would be half the distance between the foci. This would be the distance, half the distance of the major axis, or what we're calling a semi-major axis. But you see that this top and bottom number are about the same. So this is going to be getting closer to 1, perhaps maybe 0.9. Okay, now just for interest, let's think a little bit about whether any celestial objects might actually have an elliptical orbit like this? And the answer is yes. It's certainly not planets. But let me go ahead and draw the sun in here, nice bright orange or nice bright yellow. And then we'll maybe add a little more color to it with an orange. Okay, a little bit of orange right there. So there's our sun located at one of the foci. Well, it turns out, and I'll give you a little hint here, here comes an object that's traveling along here. And once it starts getting close to the sun, it starts developing a nice long tail. All right? And you can see here that tail always faces away from the sun. We'll talk about that later in class. But even as this celestial object is moving away from the sun, its tail points away from it. But what do you think that object is? That's right, it's a comet. And it turns out that comets' eccentricity are quite large. In fact, the eccentricity of comet Halley is 0.97. Very, very eccentric. Not a perfectly flat line, but very, very eccentric, much like what you see here. And we'll study that a little bit later when we discuss comets in class. And then just one more tidbit of knowledge here. We've talked about the eccentricities of planets and of comets. One more celestial object that's of interest to us, and that would be the moon. Now, Kepler's law deals directly with planets. Planets in their orbits about the sun follow an elliptical orbit. But the same thing is true with moons, such as the Earth's moon. Now, it's not going around the sun, of course. It's going around the Earth. So let's draw that right here. And we might ask, there's the Earth. That's an E. We might ask, what is the orbit of the moon? Well, it turns out it's 0.022. Now compare that with what we have up here for the Earth, 0.022. So it's a little bit more eccentric, but for all practical purposes, it almost looks like what? It almost looks like a circle. It is slightly eccentric, but yet it almost looks like a circle from looking above. Well, the point here is that Kepler's first law not only works for planets around the sun, but also for moons about their host planets. Very good. I hope this has helped you out. Good luck.